So let's say we have the integral of, I'm going to make something up that's probably not going to be nice, of 5 over x squared minus 6x plus 5. Sure, that seems fine, dx. All right. So before you even think about partial fractions, you have to ask yourself 2 questions. Well, actually maybe 3 questions. The first question is, can I do something else? This one, no. There's nothing else that we can do here, right? It's like it's just a rational function. But then you have to ask yourself, okay, if we have a rational function, does the denominator factor, and actually even before that, is the degree on top strictly less than the degree on the bottom? So you have to have the degree on top being less. If it's not less, then you have to do like division like she was doing for that one problem at the end of class. And then if it doesn't factor in the bottom, you can't do partial fractions. So it has to factor. That is a key component of being able to use partial fractions. So this does factor, right? I can definitely write my rational function. I can factor the denominator as x minus 5 times x minus 1. So it does factor. And then what we're going to do is we're going to take each of these factors and write them as the denominator of some simpler fraction with an unknown constant numerator that we're going to try and solve for. So write this as a over x minus 5 plus b over x minus 1. And then we're going to, I don't remember what she said exactly, but the idea here is that we're trying to figure out what a and b are. This fraction is equal to this fraction. We could reconstitute this fraction by multiplying this by x minus 1 over x minus 1, and this by x minus 5 over x minus 5. But what we're going to do instead is we're going to multiply both sides by the common denominator. So we're going to multiply both sides by x minus 5 times x minus 1. The point being, and again, the point always with these partial fractions decompositions is that we want to solve for these constants up here. And so the way we're going to do that is by getting rid of the denominators. So if I distribute this x minus 5 times x minus 1 to each of these 3 things, the left-hand side is always just going to be whatever this numerator is, because x minus 5 times x minus 1 times 5 over x minus 5 times x minus 1, x minus 5, x minus 1 cancel, you just get 5. And then when you multiply this whole thing times this, the x minus 5s cancel. You get a times x minus 1. When you multiply this times this, the x minus 1s cancel, and you get b times x minus 5. Now she did something that I think is good but unnecessary. So let me show you 2 different ways to solve for a and b. So what she did is called equating coefficients. It's a perfectly normal way of doing it. In fact, it's a method I use when I have to. So here's how we would do that. We would say, okay, on the left, I have 0 x's plus a constant term of 5. And on the right, if I look at this, I have an ax plus bx. So I have an a plus b times x. And I have a negative a minus 5b. So I could say plus, just to make it look like this. Okay. Right, let me double check that. A times x, a times negative 1, a times x, a times negative 1, b times x, b times negative 5. Okay, yeah. And so then here's what we do. For polynomials to be equal to each other, the coefficients of the coefficients have to be the same. So what we end up saying is we're, okay, 0 has to equal a plus b, and 5 has to equal negative a minus 5b. And then we typically isolate a variable in one of these. So we say a equals negative b and plug that in for a there. So 5 equals negative b. So b minus 5b is negative 4b. So 5 equals negative 4b. b equals 5 over negative 4. That's a fine way of doing it, but it's more work than we want to do. So here's the thing. And then you could say that A is negative B. So A would be positive 5/4. That's all good. But let me show you an easier way. So most of the time, we're going to be in the situation where we can do a different thing. If all of your factors are raised to the first power, you'll never have to do this. If you have repeated factors or an x squared plus 1, like she mentioned in class, then you do kind of have to use this. But I usually use a hybrid system where I first do the following. I pick convenient values of x, or whatever your variable is. So this is the convenient values method. So here's the deal. This equation has to be true, right? We've said that this is equal to this. And importantly, it has to be true no matter what x is. So if you go back and actually plug in like 5/4 for A and negative 5/4 for B, if x was 0, for example, 5/4 times negative 1 plus negative 5/4 times 0 minus 5, that would end up equaling 5. Because no matter what you pick for x, this has to be true. We're going to exploit that. We're going to say, well, what if I picked something convenient? What if I picked x equal to 5? Well, if x is equal to 5, look what happens. I get 5 on the left, right? There's nowhere to plug in x equal to 5. But on the right-hand side, I get a times 5 minus 1. So I get 4a, and I get b times 0. That's what makes it convenient. One of the parts is 0. So then look, a is going to be 5 divided by 4. And then the other convenient value is the other value of x that makes this part 0, which is going to be what? X equal to exactly. So plug in 1 for x, then you're going to get still 5 on the left equal to 0 plus b times negative 4. Sorry. So b equals 5 divided by negative 4, or negative 5/4. And I personally think, and I hope you all agree, that doing this, where you just say, oh, one thing's 0, one thing's whatever else is left, yeah, it's the way most people do partial fractions. Well, here's what I should really say. And it's kind of, so there's kind of a bigger picture. There's actually like 4 different subtypes of partial fractions problems. This is the first subtype, where it's non-repeated linear factors. Meaning linear factors, right? It's always ax plus something, right? There's no like x squared or x cubed. It's linear, right? It's just x to the first plus or minus a constant. And they're all not repeated, meaning they're all raised to only the first power. If that's the case, this will always work. But even if it's not the case, this is always what you should start with, because almost always there's at least one convenient value of x that's going to make something 0. So here's the result. We can then integrate this. We can rewrite this integral as, instead of 5 over x squared minus 6x plus 5, we can write it as a, which is positive 5/4 over x minus 5, plus b, which is negative 5/4 over x minus 1. And both of those things are really straightforward to integrate. This is going to be, sorry, I'm almost out of room here. The 5/4 coefficient, I kind of just ignore. I'm thinking of this as 5/4 times 1 over x minus 5. The antiderivative is 5/4 times the natural log of the absolute value of x minus 5. And then the minus 5/4. And then the antiderivative of 1 over x minus 1 is the natural log of the absolute value of x minus 1 plus c. I should mention, because, so let's say you did this problem and then looked in the textbook for the answer. In a textbook, it might show you that the answer is 5/4 times the natural log of the absolute value of x minus 5 over x minus 1 plus c. Because what they've done to simplify it and take up less room in your solutions manual is they factored out the 5/4 and then use our rule of logarithms to say the natural log of this minus the natural log of that is the natural log of that divided by that. So just be careful. Sometimes your answer, if you leave it like this, might not look like a solutions manual answer because they've often condensed it or compressed it to make it a little bit less spacious. Let's do a couple more partial fractions examples. Let me see. I want to see. Just want to make sure there's nothing I'm forgetting. I definitely wrote down a few notes here. No, I think we're good. Okay. Oh yeah, I know. I should grab the. I actually have some examples that I've already got ready to go. Sure. So let's look at this one. But the name of the game for partial fractions is really just, is the numerator lesser degree than the denominator? Actually, yeah. So does the numerator have a lesser degree, and can you factor the denominator? So let's look at this example. Yeah, let's do, sure. 4x plus 12 over x squared plus 6x plus 8. Here's what I want to say about this. Is this a partial fractions problem? Well, sure. Right, you can definitely factor the bottom as x plus 2 times x plus 4. And you can even factor a 4 out of the top, not that we need to, and get 4 times x plus 3. But here's what this problem is kind of special in that while you could do partial fractions here, partial fractions is kind of what I like to call a method of last resort. Can I do something right? Exactly. Can I do something else first? Sometimes a partial fraction is something that looks like we could for sure actually do partial fractions here, but I would much rather do the u sub that actually works here. So here you could do a u sub. U is the denominator, x squared plus 6x plus 8, and my du dx is 2x plus 6, and this times 2 is exactly that. So I can say that 2 times du is 4x plus 12 times dx. Or I suppose if you prefer, some people might actually do this instead. Some people might say du is 2x plus 6 times dx and then factor the 2 out from the top. Either way, it's the same thing. So either way, this part here is going to become 2 times du divided by u, which is just going to be 2 times the natural log of the absolute value of u plus c, which is then 2 times the natural log of the absolute value of x squared plus 6x plus 8. So before you jump to the partial fractions conclusion, be on the lookout for a u sub, because sometimes people like to be a little sneaky and hide a u sub in something that it's like, oh, partial fractions, right? Oh no, I can actually do a u sub. And the u sub is usually easier, right? Usually, right? Come on, usually. I know you guys are all laughing uproariously and you're just muted, which is why I can't hear your laughs. It's definitely the lie I'm telling myself when I tell bad puns. Okay, but now let's do the actual problem that I was going to do, which is, where'd you go? The problem is not things covering up other things. Sure. So let's look at this one. The integral of x plus 1 over x squared plus 6x plus 8. And what I want to point out here is that you should always at least be thinking, can I do the u sub? Here, if I try it, my du, if my u is x squared plus 6x plus 8, my du is 2x plus 6. That's not a multiple of x plus 1, right? 2 times that is 2x plus 2. We're out of luck. So we're going to do partial fractions. So we're going to rewrite this. Well, we can only do partial fractions because the degree on top is less, and then the bottom factors. The bottom factors as x plus 2 times x plus 4. So then we are going to say this is equal to a over x plus 2 plus b over x plus 4. It doesn't matter which one has a and which one has b. You could do yours as a over x plus 4 and b over x plus 2. It doesn't matter. I typically write the one with a, that's the one that looks like it's first. That's how I'm making my choice here. And then we are multiplying the entire equation by this common denominator. So when we do that, when you multiply this by that, you just get x plus 1. And then this times this, the x plus 2's cancel. You get a times x plus 4. And this times this, the x plus 4's cancel, and you get b times x plus 2. And now, instead of equating coefficients, which we totally could do, we're going to instead just use the convenient values of x method. So what's one convenient value of x? Right, -4. Because -4 makes this whole thing 0. So if I plug in x equal to -4, I have to plug it in wherever there's an x. So I get -4 plus 1 equal to a times 0 plus b times -4 plus 2 is -2. -4 plus 1 is -3. So -3 equals -2 times b. So b is equal to -3 divided by -2 is positive 3/2. Somebody else, what's my other convenient value that's going to make something else 0? Thanks, Catherine. Exactly. X equals -2. So if x is -2, we're going to have -2 plus 1 equal to a times -2 plus 4 is 2, and b times 0. So -2 plus 1 is -1, and then divide by 2, so -1/2 is equal to a. I will point out, because it's worth mentioning, right, what Karana is doing in class also works, right? You could alternatively say x plus 1 equals ax plus bx is a plus b times x, and 4a plus 2b is equal to, well, that's the constant term. But it's more work this way, right? You then have to say a plus b equals 1, right? The coefficient there is 1. So you have to say a plus b equals 1, and 4a plus 2b also equals 1. And then you'd have to solve them. You can do the thing where you solve for 1 and add, and then add to it, or you can do the thing where you like multiply a whole equation by -2. You can multiply this whole thing by -2 and add to that. -2a plus 4a is 2a. -2b plus 2b is 0b. And -2 plus 1 is -1. Oh, you get a equals -1/2 again. But I really hope you all agree with me that this is more work. And we're not going to do it this way until we have to. What do you mean by when we have to? Well, you'll see. Because I think, yeah, I'm definitely going to make us do at least one where we have to. That's gross. That's a lot. Yeah. I know it's an unpleasant habit, but it's one that I have. So anyway, so then after you do the partial fraction decomposition, you have to remember that you still have an integral to finish. So you have to rewrite the integral as a, which is -1/2, or go -1/2, right there, -1/2 over x plus 2, and then b is positive 3/2 over x plus 4. Often, if I happen to notice that my a and my b values are fractions with the same denominator, I'll factor that part out. So I might actually rewrite this. I'm going to erase this part here. I might, not that you really need to do this, but I might rewrite it as 1/2 times the integral of -1 over x plus 1 plus 3 over x plus 4. It's probably totally unnecessary. In fact, I don't think I want to do that. I think you could do this. I think I'd rather just integrate it. This is going to be -1/2 times the integral of 1 over x plus 1, which is the natural log of the absolute value of x plus 1, plus 3/2 times the integral of 1 over x plus 4. which is the natural log of the absolute value of x plus 4. Let's see. That's it. That's all she wrote. I'm gonna look at one quick thing here because I want to see. Someone was saying something about partial fractions in our group chat a few days ago. There it is. All right, cool. Yeah, all right. We'll do that too. So yeah, we'll get there eventually. Good times, good times, good times. Yeah, okay, we got that one. That one. All right. Let's look at this. So what if the degree on top is not less than the degree on the bottom? For example, what if we had something where even where the degrees are equal, like the integral of x squared minus 1 over x squared minus 4? Well, if this is the case, you have to do, in fact, even if it's not right, regardless of partial fractions, if you have a rational function where the degree on top is greater than or equal to the degree on the bottom, we have to do polynomial division. You can do synthetic division if the denominator is a linear factor. It's not the case here. X squared minus 4 is definitely non-linear, right? It's x squared, not x to the first. So synthetic only works if you're dividing by like x plus c or x minus c. If you have other higher powers, you can't use synthetic, which is fine. I never liked synthetic anyway. So I'm going to do x squared minus 1 divided by, I mean, synthetic's fine. It's got its uses, but it's not my favorite. So what do you multiply by x squared to get x squared? 1. 1 times x squared, 1 times negative 4. Subtract x squared minus x squared is 0. Negative 1 minus 4 is negative 1 plus 4, which is 3. And that's it. We're done. It's when your degrees are the same, it's a very much a one-step polynomial division. So we end up rewriting this. So x squared minus 1 over x squared minus 4 is equal to the quotient plus the remainder divided by the divisor. Which makes sense if you think about it, because you could rewrite 1 as x squared minus 4 over x squared minus 4, and then x squared minus 4 over x squared minus 4 plus 3 over x squared minus 4 would give you x squared minus 4 plus 3, which is x squared minus 1 over x squared minus 4. So this is definitely equal to this. And then we're going to integrate that. Well, the integral of 1 is easy. That's just x. So this is going to equal x plus the integral of 3 over x squared minus 4. Now we're in a partial fraction situation because the degree on top is less and the denominator factors. Right? Those are always the things I'm looking for if I'm looking for a partial fractions kind of situation. I have to have the degree on top being less, and I also have to have the denominator factoring. The reason I point that out is because there was one example she just did in class where she did do polynomial division, but the denominator didn't factor because there was only one term. And so you wouldn't have had to use partial fractions there, which is fine. It's just interesting. So partial fractions here. I've got 3 over x minus 2 times x plus 2 equal to a over x minus 2 plus b over x plus 2. So we're going to multiply both sides by the common denominator. You can, so after you have some practice with this, you can kind of get better at it. So like I know that when I multiply both sides by this denominator, I'm always getting that numerator only on the top, on the left. On the right-hand side, I'm getting a times the other factor plus b times the other factor. And then we pick, like all my black pens are starting to die. I'm going to replace some ink cartridges here. So we pick convenient values of x, which are going to be -2 to make this one 0 and +2 to make that one 0. So if x is -2, And be careful, right? In this previous problem, when we plugged in -4, there was an x on the left side to plug -4 into. In this problem, we pick x equal to -2. There is no place to plug in x on the left, which is okay. Just be aware. So people will try to like make an x happen on the left because they want there to be no x. So we've got 3 equal to a times 0 plus b times -2 minus 2, which is -4. So it looks like -3/4 is equal to b. And then when I try and solve for a, when I plug in x equal to +2, I'm going to get 3 equal to a times 4. It is a pretty common occurrence that a and b have it, if they're both fractions, do have the same denominator. It's usually pretty typical. All right, so then going back to the problem at hand, I'm going to erase this. This is going to equal, well, it's equal to this, which is equal to this, plus the integral of, we just decided that 3 over x minus 2 times x plus 2. Well, we didn't decide, we've determined, we found that that's equal to a over x minus 2. So 3/4 over x minus 2 plus b, which is -3/4 over x plus 2. Instead of writing plus -3/4, let's just write -3/4 over x plus 2. And then we integrate that. And so most of the time, when you're integrating something over x plus or minus a number, you're just going to get natural log of the absolute value of whatever's in the denominator. It's slightly more complicated if x has a coefficient, but we haven't seen that yet. At least not in these examples. So here we're going to get x plus the antiderivative. That's going to be 3/4 times the antiderivative of 1 over x minus 2 is the natural log of the absolute value of x minus 2. Minus 3/4 times the antiderivative of 1 over x plus 2 is the natural log of the absolute value of x plus 2, plus c. And again, you could totally condense these two natural log terms since they have the same coefficient. You could factor out the 3/4 and write this part as 3/4 times the natural log of x minus 2 divided by x plus 2. But I wouldn't worry about that too much. Okay. Yeah, I definitely had 2 more examples I wanted to get to. So I will point out that someone in class asked about what if you have something that's not like x plus 1, if you have like x squared plus 1. And I think she said there was some example that in the book that you could look at that would help you with that, which is perfectly fine. But let me just tell you, so here's the deal. You have to know what the integral of x squared plus 1 over x squared plus 1 is. What we've definitely talked about, the integral of 1 over x squared plus 1 is everybody's second favorite inverse trig function, arctangent of x. You're probably going to want to remember that. And it's also probably in the integral table she was talking about in the second half of class, or the last like 15 minutes of class. And more generally, if you integrate like 1 over x squared plus, say 25, well, now I have to remember what it is. It's 1 over 5 arctangent of x over 5 plus c. Or more generally, if you're integrating 1 over x squared plus some number squared, it's, or that's a, it's 1 over a arctangent of x over a. So if this sort of thing pops up in your integral, then you have to remember that its integral is this. So let's look at an example of a partial fraction where that's going to happen. Gosh. Yeah. So the problem here is that there's a lot to say about partial fractions, and I don't want to say more than you need to know. Not because I don't think you should know it, just because I don't want to waste your time. So I'll do this one example. So let's do the integral of 1 over x, the integral of x plus 1 over x cubed plus x dx. So degree on top, less. Okay, do a u sub? Probably not, right? If u is x cubed plus x, my du would be 3x squared plus 1. Doesn't look like it's going to work out nicely. So does the denominator factor? For sure. I can write this as the integral of x plus 1 over x times x squared plus 1 dx. And that's all the factoring that happens. Now, here's the thing that's kind of special. For our regular factors, where for the linear factors we've had, where like x minus 2, x plus 2, x minus 1, x plus 3, right? All those are linear factors, right? There's some mx plus b. But that's not a linear factor. That's called an irreducible quadratic factor, right? It's a second degree factor, and it's irreducible, meaning it cannot be factored any further, right? We can't factor x squared plus 1. At least we can't factor it without using imaginary numbers, right? There's no real numbers you can use to factor x squared plus 1. So irreducible quadratic factors are extra special when it comes to partial fractions. To write the partial fraction decomposition, the linear factor x still gets treated normally. You get an a over x. You get a constant over a linear factor. But for an irreducible quadratic factor, you don't get a constant on top of it. You get a linear factor on top of it, or a linear numerator. You get not just a b, you get a bx plus c. The reason for this is because the math doesn't work if you don't do this. So if you try and reduce this as a over x plus b over x squared plus 1, you'll get like the a is equal to 0 and a is equal to 3 or something weird like that, because you can't decompose this into these factors without having the extra piece on top. I can say more about that in office hours or another time, but I don't want to kind of waste your time with that small detail. Just know that if you get faced with something like an x squared plus 1 or an x squared plus 4 or an x squared plus 9 or an x squared plus 7, the x squared plus number has to have this kind of thing on top of it. Ax plus b, bx plus c, whatever letters you're at, letter times x plus next letter in the alphabet. You need all of that. And then we're going to do the usual stuff. We're going to multiply both sides by the common denominator. So I multiply everything by x times x squared plus 1. On the left, I get just x plus 1. On the right, I get a times x squared plus 1 plus bx plus c times x. And now you might notice there's only one convenient value of x. We're still going to use it. What is it? What's the value of x that makes things go away? Don't say the square root of -1. I'll break you. There we go. So the value of x that makes stuff go away is 0, right? If x is 0, all of this disappears. So my only convenient value of x is x equal to 0. So I pick x equal to 0. On the left, I get 1. On the right, I get a times 0 plus 1 plus b times 0 plus c times 0. 0, right? 0, yeah. So a equals 1. But here's the thing. We're out of convenient values now. If there's no other value of x that's going to make a bunch of stuff 0. So this is where we do go back to the method she was using for all of her partial fractions, where we're going to equate coefficients. So if I look at this, let's see what I'm going to rewrite my equation. So on the left-hand side, I have a 0x squared plus 1x plus 1. On the right-hand side, let's see, I have an ax squared and a bx squared, right? This distributes here. So I have an a plus b times x squared. And then let's see, I have a c times x, right? That's my only x term. And I have an a times 1, and that's my only constant term. So check this out. We actually probably could have just equated coefficients here and been right. I still think it's worth your while to use whatever convenient values of x you've got. So look at this. A has to equal 1. Well, that's good because we definitely had a equal to 1. C also has to equal 1, right? Because the coefficient of x has to equal the coefficient of x. And a plus b has to equal 0, but we know that a equals 1. So 1 plus b equals 0, so b has to equal -1. Questions about this? All right, so here's what we've got. We've got our partial fraction decomposition. I'm just going to erase this part and write it out. This is equal to 1 over x plus -x plus 1 over x squared plus 1. And that's what we're going to try and integrate. Okay, so I'm going to leave this here for a moment. I'll just do it on the other side, so we can come back to this if you guys have any questions about it. So we're trying to integrate, let's see, 1 over x plus -x plus 1 over x squared plus 1. And here's the deal. Whenever you have one of these irreducible quadratic factors and you've got multiple pieces on top of it, you always have to break it up into 2 pieces. I really should have written it as bx over x squared plus 1 plus c over x squared plus 1. That's what I really want. So this is really the integral of 1 over x minus x over x squared plus 1 plus 1 over x squared plus 1. And now here's what's going to happen. We know what to do with this. The integral of that's going to be the arctangent of x. This is going to require a u substitution, and this is going to be the natural log of the absolute value of x. So let's over here on the side, let's do this middle part real quick. So the integral of x over x squared plus 1, I'm going to let u equal x squared plus 1. Du is 2x dx. 1/2 du is equal to x dx. So this becomes 1/2 du over u, which is 1/2 the natural log of the absolute value of u, which is 1/2 the natural log of the absolute value of x squared plus 1. Whew. Okay, so that means the integral of this part is 1/2 the natural log of the absolute value of x squared plus 1. So here's what we're going to get in total. Natural log of the absolute value of x minus 1/2 the natural log of the absolute value of x squared plus 1 plus the arctangent of x plus c. This will probably come up, so be aware of it. It's not a guarantee though. God, I don't care. Sorry. Yeah, we're probably not going to get to do too much U7 and integration by parts today, but definitely Friday we can circle back around, because I know I definitely looked at your homework assignment and it's a lot of U7 integration by parts. Let me do one more partial fractions because there's one other kind of special case that comes up, and then we will move on. And this special case actually is important, even though I don't think they talk about it a whole lot in your class. There definitely are times in 17C when you're solving, what's the word I'm looking for? In fact, where'd you go? Yeah, when you're solving differential equations where you actually have to use this next thing. So let's say I want to integrate 1 over x times x. Fine, I'll do a little more. Let me write it this way. 1 over x cubed minus 2x squared plus x dx. I want to integrate that. clearly, maybe not clearly, I don't know. Definitely the degree on top is less than the degree on the bottom. Clearly factors, I mean, yeah, you can definitely factor out an x, which is enough to say it factors. And then I'm left with x squared minus 2x plus 1, which does factor further as x minus 1 times x minus 1, which is x minus 1 squared. So this is an example of a repeated linear factor. I have x minus 1 times x minus 1. So the x minus 1 factor, which is a linear factor, is a repeated linear factor. So when you have a repeated linear factor, you need all the lesser powers of it in addition to whatever the highest power is. So if I'm going to try and write my partial fraction decomposition, holy smokes, 1 over x times x minus 1 squared, I'm going to write it as a over x plus b over x minus 1 squared, and then every smaller power of it, plus c over x minus 1. And I will be honest, usually I write my powers in ascending order. I usually write it as b over x minus 1 plus c over x minus 1 squared. But basically, you need these terms, whatever your factors are in the denominator. And then if you've got something raised to a power like this, if you've got a repeated factor like this, you need all the lower powers of it also. So just for argument's sake, like if you had something stupid, like the integral of, I don't know, 1 over x cubed times x plus 2 to the 4th, we're not going to do this one, but if you were going to write out the partial fraction decomposition, it would need 7 pieces. You'd have to have 1 over x cubed times x plus 2 to the 4th equal to a over x plus b over x squared plus c over x cubed plus, and then you need 4 for that, right? You need d over x plus 2 plus e over x plus 2 squared plus f over x plus 2 cubed plus g over x plus 2 to the 4th. So that's what I mean. If you have something that's raised to a power, you need that power and every lesser power down to the first power of it. Okay. No one should ever give you a problem like this. This is totally dumb. So then we're going to do the usual thing. We're going to multiply both sides by the common denominator. I'm going to get 1 when I multiply this by x times x minus 1 squared. When I multiply this by the denominator, the x's cancel. I'm left with a times x minus 1 squared. When I multiply this by the denominator, the x minus 1 squared cancels, and I get b times x. When I multiply this by the denominator, one of the x minus 1s cancel, so you get c times x minus 1. Okay. Now we're back to, I want to pick convenient values of x. Somebody tell me one of the convenient values of x. What's something that's going to make lots of things 0? Sure. Somebody else tell me one of the only other convenient value of x. Thank you. So x equal to 1. I plug in 1 for x, and I get 1 equal to a times 0. Not even going to write it down. B times 1, c times 0. Great. B equals 1. How nice. For x equals 0, again, when I'm plugging 0, so I'm going to get 1 equal to a times negative 1 squared plus b times 0 plus c times 0. So a equals 1 also. How convenient. Now, for the last, so we're out of convenient values. I still have to find c. Here's what I'll say. I personally like to use the method of equating coefficients, which is what you do when you say like whatever, like what we did. Sorry, I erased it. Yeah, what we did when we say like the coefficient of x squared has to equal the coefficient of x squared and so on. But if you prefer, this is only really good when there's only one thing left to find. If you only have to find c, you could say, well, a is 1, b is 1, and I can pick any other number for x, plug that in, and then solve for c. That's not what I'm going to do, but it is something you can do. I would prefer to just say, well, how much x squared do I have? So I actually don't even like to write out the whole equation with the coefficients. I just like to look at one particular value, one particular power of x. Usually the highest power of x is the most convenient. So let's look at x squared for a second. How much x squared is on the left side of this equation? 0, right? There's no x squared over there. How much x squared is on the right side of this equation? Well, let's take a look. If I multiply this out, it would be x squared minus 2x plus 1. So you're close. It's not quite 2, Emily. It's actually going to be a times x squared plus a c times x squared. There are 2 instances of it, but the coefficients are a and c. So it would actually be a plus c times x squared. The real answer that I suppose is what I could say, there's actually has to be 0 x squared on the right side, since there's 0 x squared on the left side, right? They have to be the same amounts of x squared. But specifically, the expression for the amount of x squared on the right side is a plus c times x squared, which tells me that a plus c has to equal 0. And since we know that a equals 1, c has to equal -1. That's what's happening here. Yeah. So then we would do this integral. It'd be the integral of a over x. So 1 over x, right? A is 1 somewhere, yes. 1 over x. And then b is 1 over x minus 1 squared. And then minus 1 over x minus 1. Just about out of time. So let me finish this integral. I don't want to erase what I wrote because I feel like you guys must be looking at it. I'm going to erase what I wrote. I will point out before I erase this, the important part of this decomposition is making sure that for the x minus 1 to a higher power, you have that higher power and then all lesser powers in each of their own terms. So basically, if you have an x minus 1 to a power, you should see that many different fractions that have different powers of x minus 1s. Okay, now to integrate this, okay, the integral of 1 over x is the natural log of the opposite value of x. The integral of minus 1 over x minus 1 is minus the natural log of the opposite value of x minus 1. The middle term is not going to be a natural log, right? We don't have 1 over x plus something. We have 1 over x minus 1 squared. So the thing about this is you could do one of 2 things. You could do a u sub. In fact, I'm probably going to do a u sub. So for the integral of 1 over x minus 1 squared, you can let u equal x minus 1, and then du is equal to dx. So this is going to be the integral of 1 over u squared, which is the integral of u to the minus second. So we're really just using the reverse power rule here. That's going to be u to the minus 1 over minus 1, or negative 1 over u, which is negative 1 over x minus 1. So that's what we get for the integral of that part there. I don't think you actually have to do a u sub there. You can just say, hey, look, I've got the integral of x minus 1 to the negative second, and I can just use the reverse power rule and get x minus 1 to the negative first divided by negative 1. And I don't have to worry about adjusting because the coefficient of x here is just 1. So, right, if your u is x minus 1, you almost really don't have to actually do the u substitution. But you can if you want. And then I would probably write this like this, and then plus c.